expecting. So, well, I was kind of tempted to play with this word, of course, like showing some shower of smartphones or something like this. But I don't know. Probably I should have. Anyway, so the idea of this talk is that, well, while we have heard about several programs and research directions and so on, to well, so it's going to be a little bit orthogonal to that. So I'm going to talk about a method that hopefully can be used for our counting, specifically approximation counting problems. Well, this all is about invariants, of course, and well, it has been quite successful in other areas. So empirically, so far, if you look at various kinds of constraint problems, well, whenever you have something like this, you can get general results. I don't know if it's a coincidence or not, but generally this is what's going on. So once you develop an approach like that, you start getting some general results, not before that. Well, there are exceptions, of course, and limitations, but nevertheless. So the hope is that, well, we might be able to develop something like this for approximate counting, and then, well, we kind of flood the world with our brilliant results. Okay. So, well, this is why actually I will mostly be talking not about counting rules. So the approximate counting will occur in the very end. But I want to sort of put everything in a wider context. So, what are we going to talk about? Well, I will always fix some finite set of elements, spins, values, whatever your favorite word for that. Sometimes I will be interested in relations. Well, we all know what a relation is. Sometimes it's convenient to look at relations as 0-1 functions, of course, like predicates, for instance. Well, sometimes I will mean not relations, but kind of proper functions. For instance, if I'm talking about optimization, these in most cases will be some sort of real valued functions. Well, if I'm going to talk about partition functions, or then this will be non-negative or positive functions. I don't want to make so much distinction between these two, because it's exactly the point that there is no so much difference. And so I will use the same symbols for relations and functions. Hopefully, well, I will confuse enough people with that. But nevertheless, so hopefully it will be clear from the context what we are talking about at the moment. Okay, so what is the general framework? Constraint problems. Well, this is what all people here are doing, in a sense. So what we have, well, we have some sort of a bunch of variables. Right? Well, variables take some values, again, spins, elements, whatever you want. And we have a bunch of constraints. So constraints here can be relations. Well, by the way, this S1, SQ are just sequences of variables from V. So constraints can be relations. Well, they can be functions, whatever. Whatever we are talking about, well, the corresponding notion of constraint we have to use here. Well, very often we will assume that all those constraints, these relation functions, belong to some fixed set we are interested in for whatever reason. Well, in this case, I will talk about the instance of a CSP of gamma. So some people, especially in AI, call this a constraint network. Well, we can talk about constraint networks if we want, or constraint instances again, whatever. Okay, for instance, if I have just one binary relation function, then this is what we have, right? We just have a graph with all this function imposed there, so we may have an instance of an isn't model or something like this. If we have more than one binary relation, we may think about something like this. Again, same graph, it may be labeled with different with different functions relations, but nevertheless, the overall concept is more or less the same. If we go a little bit more general and think about not only binary but ternary, fourier, and so on relations, well, we may have a hypergraph, right? So, for instance, here I have a ternary relation imposed on this, or function imposed on these three variables. This one is binary, of course, and so on. Hopefully, I'm consistent with indices, right? So R1 is ternary here, and it's ternary here. So it seems okay. Right. Now, what do we want to do from such a constraint network? Again, it depends on the problem we are trying to solve. So this is our instance. If we want to solve a decision problem, which is the CSP, constraint satisfaction problem, well, then we are looking for a assignment of variables with values or something like that, an assignment that satisfies all the constraints. So this means that this constraint relation is satisfied. So if I take the variables, take the corresponding tuple of values, well, it belongs to the relation. It belongs to the relation. So in this case, we are talking about relations. Well, if we want to optimize something, then, okay, again, we are maximizing overall possible assignment, and we view this constraint network as the cost function, and we want to maximize it. And we want to maximize this cost function. In this case, we are summing up the values of the function over assignment, and we want to find an assignment that makes it as large as possible. Well, in sort of combinatorial or unweighted counting, we want the number of solutions like that, satisfying solutions. Well, if we compute in partition functions, then, okay, instead of summing here, we have to multiply and then sum up. So basically, if you look at these, say, four options, the only difference is what kind of aggregation operation we use. For instance, here we just use what? We use conjunction first, right? All of them must be true. We use conjunction first and then maximization second, right? If we use conjunction, then we have a solution if and only if the maximum is 1. And if maximum is 0, there is no solution. So conjunction, then maximization. So here we use summation, then maximization. Here we use what? Conjunction and then summation. And finally, okay, product and summation. Well, this is the only difference. The only difference is just this aggregation operation.
Are you only considering the case where the set A is fixed size, or are you?
Yeah, well, I fixed, say, A in the very beginning, and I assume it's
V is...
V can be large. V can be large. Okay, if we fix our set of allowed constraints, well, we may have decision problem. Well, normally this is denoted VCSP, it's valid constraints, but since we want to maximize the value, I believe it's fair. Well, actually, I'm sort of making up notation and terminology as I go. Well, this is because there is some sort of disarray in, and more than one people in this room actually contributed to that disarray, but anyway, well, and that's counted. Okay, good. So this is basically what we want to do. Well, the overall problem, the ultimate goal we want to achieve is we want to classify the complexity of such problems. Decision, valued, counting, well, optimization problem can be classified, well, the complexity of optimization problem, well, can be in two possible meanings, exact, approximate, and same here, exact, approximate, counting. Well, what is approximate decision, I don't know. Okay, so how do we do that? Again, normally if we want to sort of study complexity on a large scale, we want some kind of reductions between problems. With CSP, there is very clear connection with the most popular way of reducing problems to each other, through gadgets, of course. Okay, so what are gadgets in terms of CSP? Well, it's a very simple and very natural thing. Suppose I want to express, well, I'm not saying what express means right now, but suppose I want to express some function relation R through some other functional relation. So what can I do? Well, suppose this one is binary and the one I am going to use is also binary. So what I can do? Well, I can construct a small graph, for instance, and say, well, on every edge of this graph, I impose this Q. Then I hope that if I only look at the terminals of the gadget, well, somehow it represents R. And again, the idea is that if after that I take my constraint network, plug in the gadgets instead of R somehow, then I can tell something meaningful about what I get. Right? So the hope is that if there is such a gadget in whatever sense, then CSP of R, what I represent, it is reducible to CSP of Q. So if we look only at gadget reductions like that, well, again, I don't specify right now in what sense it's reducible. It can vary from problem to problem. But the overall idea is that all the gadget reductions look very natural in CSP. Okay, let's look sort of at in a more detailed way. So let's look how exactly we can use gadgets depending on the problems. Well, one very general way, also not very interesting, is just use no auxiliary variables. So let me explain what I mean by that. Suppose this is my gadget, right? Again, I use this binary relation Q, and I hope to express relation R. But now, what I have here must be the relation R. So everything, there are no terminals. Every vertex is a terminal. Right, so in this case, R would be 6 array, and Q is binary. And in some sense, R is defined by this binary interaction of values and so on and so on. So that would be the easiest and simplest way. I can say that I represent a new function relation as an instance of the CSP, of the constraint problem. So if I have something like that, then the reduction really holds. There is a reduction in all possible meanings we can think of. So that is a very kind of straightforward and very general. Well, if you think about it, every time I have R, I just plug in this gadget. I don't have to change anything, and I get a constraint network over Q rather than R. So there is no change at all. Such reduction exists whatever I do here. Okay, so more generally, if I have R and gamma function or whatever, then and there is an instance of CSP of delta. So delta is some other constraint language, such that using some functions relations from delta, in the decision case, I can express my new relation as just disjunction of everything. Well, in that case, CSP of gamma is reducible to CSP of delta. So if I can express every relation from gamma this way, then I have a reduction, and gamma is easier than delta. Well, in optimization case, well, I have to do something like that. Again, this is what we mean by the goal of the CSP in these cases. Okay, so I'm just summing up. Well, then I get a reduction here. In the counting case, okay, I have to multiply. So whatever I'm supposed to do in the CSP, I do here with the gadget, and I immediately get a reduction between the problems. Okay, very conveniently. Very convenient. Right. So, well, let's look at a small example. Suppose I take a relation which is represented by a gadget like this. So it's just a triangle. My relation R will be ternary. I have 3 vertices. All of them must be variables of R. And I impose the disequality relation on every pair. What do I get? Well, it's very easy. If my set A is 2-element, then clearly R is just empty. I cannot make 3 different elements out of 2-element set. Well, if it contains more than 2 elements, well, this is the relational different. It doesn't look like a big deal, and actually it is not. It's kind of very weak way of reducing things. Okay, so anything more complicated? So another piece of terminology, of random terminology. If I have some constraint language delta, I take all functions of relation that can be expressed by instances, well, in the sense I showed on the previous slide. Then I say that this set is called a weak clone generated by delta, and I will denote it like that. So the idea is, whatever I have inside this weak clone, I can reduce to CSP of delta. Whatever I have here, I can very straightforwardly reduce to CSP of delta. Okay? Something a little bit more sophisticated, something a little bit more complicated. Say, what if I look at the decision problems and try to use some auxiliary variables? Well, in the quantification case, what I have to do is this. I'm trying to express some relation using this constraint language delta. So what do? I take an instance of CSP of delta, this constraint network, right? And then I quantify away some of the variables. So I say, okay, my relation is true here if for some values of the auxiliary variables, this all is true. So nice thing again is that there is a reduction still between the decision CSPs in this case. There is a reduction between decision CSPs in this case. Okay. Well, that was first observed by Givens and other people, well, almost 20 years ago. Also, well, it's very simple. It's nearly trivial. Okay, again, well, I need the set of all functions that can be expressed this way. I will call it a clone and denote this way. Well, so this usually denotes this weak clone, what I can express just by instances, and then whatever extra operation I use, I will just put it as a subscript. Okay, so in this case, it's quantification. Again, a small example. So suppose I'm trying to construct a new ternary relation only now this way. So these are the terminals. Right? I again impose a disequality relation. So now what happens? Now I have to look at those values of x, y, z that can be extended to a value of this extra variable so that all constraints are satisfied. Right? Well, and clearly what it is. It's clear what it is. Of course, if I take, say, three-element set, then this is exactly all tuples that are not all different. So this way we can express something more interesting. Now it's not rather than all different, it's the complement of all different. Okay. What about optimization? Well, same thing, very quickly. So again, we can introduce this notion of clone for optimization, well, maximization in this case. Well, rather than quantify things, I have to maximize away some variables. So I have to take the maximum value, well, for all possible extensions of my tuple. Again, if same things happens. If everything can be represented like that, then there is reduction between problems. Okay. Again, a small example. Let's take some familiar function like Fraser. Right? This means that it's a value of 0, 0, 0, 1, and so on. Of course. If I take this gadget, which is called stretching for whatever reason, and say I put this Fraser on both edges of the gadget, what do I get? Well, let's count. So if both x and y are zeros, right, then I can put either 0 or 1 here. I have to compute the value of the whole thing in both cases and take the maximum. Say if this is 0, this is 0, I assign 0 here. This one is going to be lambda, this one is going to be lambda. This one? If this is 1, so I have 0, 1, 1, 0, both equal 1. Both equal 1. If the values are different, clearly whatever I assign here, at least one of the two, for at least one of the edges, For exactly one of the edges, the values are different, and therefore, in one case, for one of them the value is lambda, for the other one the value is 1. Right? So what I express is something like this. What I can express is something like this. This is basically also Fraser function. Well, we can observe that the parameter here is somewhere in between 1 and lambda. So it's kind of a little milder Fraser function. Right. So that's what we can achieve by using this maximization thing. Okay. What about counting? Exactly same thing. The only thing that changes is just this sigma instead of max, and I have to multiply rather than sum up. So nothing changes. And again, I have a reduction, of course. And again, of course, I have a reduction. Interestingly, though, in this case, we can go a little further. If we are dealing with relations rather than functions, we can prove a slightly stronger result. So that is very simple. It's basically trivial. This is basically trivial. But you can replace sigma here with quantification. And that is stronger. That allows to use some different tools that, well, she will probably talk about later a little bit and so on. So that is already non-trivial. But nevertheless, we would like to see that rather than that. This is weak, and this is stronger. Okay, again, small example. Say, let's take an implication. Well, that's the truth table of implication, if you remember. Actually, I teach almost every year this discrete math 101. And in that, in the final exam, I usually try to give some kind of convoluted problem on implication, basically on the definition of implication. And every time, sort of 95% fail this test. I mean, well, this specific problem, I don't know why. So that's look very simple. This is why I thought that it's a good idea to sort of reproduce it here. Who knows? Okay. Let's try to express something new, and I do it this way. So I take two terminals like this. I put this little graph, and I impose implication this way. Well, actually, Leslie gave a very similar this example, more complicated example than that, in her presentation. And what we are supposed to get is very clear. So if I put equal values on x and y, say 0, 0, what happens then? If both are 0, the value of this one should be 0 as well. It must be 0. But I have freedom at this vertex, right? It can be 0, it can be 1. So generally I have two ways of extending x and y onto the two extra variables. So the value should be 2 if these two are 0, 0. For 1, 1, it's the other way around. It's, this one is forced to 1, and I have freedom here. If the values are different, then, well, this must be 0, and there is no other way around. And, well, there is no other way, and this must be 1. So what I actually get is a function like this. If the two things are equal, I get 2. If they're different, I get 1. So this is a Fraser function. This is a Fraser function. Okay. Good. So next step. Well, this all is good. We all know that, and sort of in the complexity course we master such things. But, well, the real trick is to go one step further. What we are going to do is we are going to try to find some dual properties that would sort of respect or preserve these gadget reductions. These will be polymorphisms. Again, I'm going to give several versions of polymorphisms. Terminology is in disarray. So if you want to find any connections to other works, it may be non-trivial because, well, the different works disagree on terminology and notation. But okay, what can I do about it? Right. So what is polymorphism? Well, everything originated in the decision problem, in decision CSP. This is where all this technology works its best. It's really everything is very clean, everything works fine, and so on. It's definitely very useful. And then as we depart from decision problem and go to optimization, counting, and so on, well, this property will sort of getting weaker and weaker, but still something will remain somehow. Okay, so what are we talking about? Suppose I have a relation. So R is a relation. I say that a function operation on the same set, possibly multi-array, possibly of several variables, is a polymorphism of this relation if the following thing happens. Whatever tuples I take from my relation, if I apply the function component-wise, I again get a tuple from the relation. So if I apply a function in any way I want, the relation is preserved. Well, we may think of it as some kind of high degree or high order symmetry of the relation. Right? So this polymorphism sort of moves the relation around, but nevertheless, it is preserved. Well, for the set of all polymorphisms of a single relation or a bunch of relations, I will write pole of R, pole of gamma. Okay, what is good about them? I will give a couple of examples of polymorphisms in the next slide, but just let's finish with this kind of more general stuff. What is known about it? What is known is that polymorphisms describe precisely gadget reductions in decision CSPs. Just 100%, very, very exact. So if I can express R, then this is because R has all the polymorphisms of gamma. Well, it may have more, but it definitely has all the polymorphisms of gamma. So in some sense, gadgets, what I can get using gadgets is captured by polymorphisms, 100%. Very, very exactly. Very exactly. Okay, well, this means that if I have some inclusion between polymorphism of constraint languages, then I also have a reduction between the CSPs. Well, it should be the... Right, so if this one has more polymorphisms than gamma, this means that it's sort of smaller, right? It has more symmetries. So this one is bigger, this one is smaller. And so, yes, CSP of delta is reducible this way. Okay. Same is true for counting problems. For exact counting unweighted, okay. To be more precise. Okay. Couple of examples. Say I take a relation like that. So just 3 pairs, 0, 1, 1, 2, 2, 0. My base set has 3 elements. And my function is this x minus y plus z, where plus and minus are modulo 3. So I'm claiming that f is a polymorphism of R. Why is that? Oh, okay, what am I supposed to do? I'm supposed to take some pairs from here, apply the function component-wise, and check what I get. Right? For instance, I take all the 3 pairs, say in this order. Well, it may depend on the order in which I take them. Well, let's count. So 0 minus 2 plus 1. I think it's 1. 1 minus 0 plus 2, of course it's 0. 2, 0, it's there. Okay, I have to take some other combination. For instance, I take 0, 1, 2, 0. They don't have to be different, right? So I can take 0, 1 again. 0 minus 2 plus 0 is 1. 1 minus 0 plus 1 is 2. Okay, and I have to do all such checks for all possible selection of pairs. Okay. Well, oh, by the way, why this is true, it's because this is a coset of a subspace of the 2-dimensional linear space. So actually this function exactly preserves such cosets. That's a non-trivial fact, but nevertheless, well, it's easy, also not trivial. So sometimes polymorphisms capture kind of nice properties of relations. Okay, well, some other property. For instance, if I have a majority operation, which means that whatever x and y are, if I, well, okay, it acts out like majority. Right, so it takes the majority of its values. In this case, if I have a relation invariant, okay, if it preserves some, if this is a polymorphism of some relation, terminology, then this relation is basically defined by its binary projections. So a tuple belongs to the relation if every pair of entries belong to the corresponding projection of R. So in some sense, in this case, R can be represented as a single instance without any quantification from binary relations. So this can capture this property as well. Polymorphisms can capture this property as well. Okay, some results. The dichotomy conjecture for the CSP, well, roughly speaking. CSP is polynomial time solvable if and only if gamma has a non-trivial polymorphism, otherwise it's NP complete. Well, so one of the dichotomy conjectures, well, it's proved in many special cases. It's still open in general. But, well, Ginny was saying that in order to have a polytime algorithm, something beautiful has to happen. Well, I have a precise definition of beauty for you. Polymorphism is beauty.
Beauty is in the eyes of the beholder.
What's that?
Beauty is in the eyes of the beholder.
So, same happens for exact counting. Well, I believe she will be talking about exact counting, but, well, he will probably represent it in a different way. But still, the exact counting dichotomy theorem in this case can also be captured by polymorphisms. So it works just nicely in this case.
True.
What's that?
What you just wrote.
What do you mean?
It can be described.
Yes, yes, it can. Well, I mean, I don't know how, but it can. So there is a property of these things that captures exactly that, but we just don't know the property. Or at least we cannot express it in a concise way. Okay, what about optimization? Well, for optimization, things are a little bit more difficult, of course. So let's first talk about the exact optimization. A morphism for optimization, well, there are several versions, but let's start with the simple one. Well, actually, properties like this will show up for approximate counting as well, so we better cover that to some extent. The simplest one is multimorphism. Also, multimorphism already sort of suggests that it's not very simple. Well, again, I have this set. I take some operations on A. Some operations on A. Then I say that this collection of operations is a multimorphism of some function R on the same set. If for any collection of, well, if this one is K array, then this should be K tuples as well. The following condition holds. If I take the sum of values of my function on these things separate, and then I apply all these operations to all these things component-wise, and then compute R, that I have to get something smaller. I have to get something small. Well, that is kind of not very easy to understand what it means exactly, but well, the idea is after we apply this multimorphism, we get something worse, not better. Right, so we would prefer this, not this. Right. Well, there are very nice, very fine examples of multimorphisms. For instance, submodularity. If my set is, say, 0, 1, as M1 I take the conjunction, as M2 I take disjunction, then my condition, well, transforms into something like that. And this is exactly the submodularity condition. And it's one of the, it's extremely well studied, and this is one of the few known reason to be for optimization problem to be solvable in polynomial time. So that is a very well-known condition, and it's very important.
Can I ask a question?
Yes.
What do you mean by non-trivial when you talk about polymorphisms?
Non-trivial. Okay, so officially a trivial one is so-called projection or dictator. It's an operation that always takes the value of the same one of its arguments. Say f of x, y, z always equals y. That is a trivial one.
So I could imagine like taking my decision problem doubling it.
Right.
So now I have like a disjoint union of two copies of basically the same decision problem. And then thinking about the polymorphism that swaps variables.
No, well, the polymorphism acts on values, not variables. On values. I'm always talking about A, which is the set of values.
I see. This is more like a multimorphism or something.
Well, it's the same. It's the same idea. So some transformations of the set of values.
But I feel like I can always create something with sort of a non-trivial looking polymorphism, but then I just mod out by it and I get back to the original thing by just creating copies and then like permuting them.
Well, copies don't help. Copies don't help
I know,
because
it
actually
help the complexity at all, right? But it produces some system that's like that has this.
okay. So let's go back, for instance. Well, to my result, like this one, for instance. So suppose I have this polymorphism. This means that whatever relation you have, it has to be expressible by a system of linear equations. So the claim, well, the precise claim in this case would be, if I have this polymorphism, your CSP is just solvable by Gaussian elimination. So that's how it works, more or less. So every polymorphism gives you some kind of non-trivial property of relation that you can use to solve your problem quickly. That's the idea. Well, yes, what this property is exactly the problem. So how we can use that property to construct a polynomial time algorithm. That's exactly the problem that everybody is trying to solve. Okay, so multimorphisms, well, submodularity. Well, we can generalize that. So that's not all. It doesn't capture exactly the complexity of optimization CSP. So we can go a little bit further and construct things slightly more general. So instead of multimorphisms, we can use fractional polymorphisms. Is it the current official term? Fractional polymorphisms? Well, it was 2 days ago, so it should be. So what do we do? We again fix this base set, like the set of spins, and consider all operations, say k area operations on this set. It's big. If you count how many operations there are, it's it's the size of A to the power of size of A to the power of k. So this set is big. This set is big. So all such operations. Okay, then I take a probability distribution on this set. So it's a big set. I take a distribution on this set. So mu. I will call this distribution a fractional polymorphism of a function, say a real valued function. Well, if something similar to those multimorphism happens, the expectation, which is a probably glorified way of representing a weighted sum, of course, should be less than the average of just summing up the values of the functions. So if you compare with multimorphism, it just means that my distribution is 0 everywhere except for those M1 and so on. For instance, for submodularity, k equals 2. I'm talking about binary functions. I assign, in my distribution, I assign probability 1/2 to conjunction disjunction and 0 to everything else. And well, this is what I get from the inequality. So what is good about that? Okay, first of all, again, if I take the set of all such fractional polymorphisms, then it describes exactly, precisely the gadget reductions between optimization problems. So first of all, it describes precisely the gadget reductions between optimization problems. And we can use it. Again, this thing is solvable in polynomial time if and only if there is a non-trivial, also non-trivial in this case is slightly different. I don't want to go into details. A non-trivial fractional polymorphisms, otherwise it's hard. Okay, so several people involved and so on. Again, the same thing. non-trivial polymorphism means a good algorithm. No such polymorphism, no algorithm. Okay. What about approximation? Again, optimization, but now approximation case. It's very similar. So again, well, I don't expect sort of everybody internalize these things, but nevertheless. So it's kind of very similar. Again, I take a distribution over all possible operations on the set A, and so on and so on. But now I have one more parameter, alpha, and I am talking about alpha approximation polymorphisms. Well, if you compare the inequalities on the previous slide and this one, there are basically two differences. First, this alpha here, and the sign is different. It's the other way around. It's the other way around. Well, clearly they somehow go together, of course. Again, I don't want to go into details of that, but the main thing about this is that using this, well, we can classify all the complexity of all approximate complexity of all optimization problems. For instance, if for a constraint language gamma, let alpha gamma is the greatest constant such that there is a non-trivial, in yet another sense, alpha gamma approximation polymorphism, then, well, here we have to make an assumption, more precisely the unique games conjecture. Alpha gamma is the approximation threshold for the CSP, meaning that there is an algorithm that approximates it this well, but there is no algorithm that approximates it better. The interesting thing about this is that, okay, the solution algorithm here is semi-definite programming. What happens is that such polymorphism actually gives you a rounding scheme for this SDP. So in a sense, in this case, polymorphism is the algorithm. So previously we have, okay, well, we can exploit this property in this way or that way, but here everything is very simple. Polymorphism is the algorithm. Okay, so finally, approximate counting. I still have a few minutes. Talk about approximate counting. So first of all, again, let's follow the same scheme and see how far we can go with that. Clones. Well, it's counting, so we can use the same sigma clone, so this summation is allowed, but since we can approximate, we can also use limits. What it means? This means that if I have a sequence of functions that all belong to that clone sigma, then I can take the limit of those functions, right? Pointwise limit of those functions, and well, I can approximate well enough to simulate problems with this R. So this will be my omega clones. Okay, what we know, again, well, it's not that difficult to show that if I have a gamma in this omega clone, that the counting CSP is AP reducible to counting CSP of delta. Can we find any morphisms? Morphisms in any sense? Well, actually, yes, we can. The problem, how good they are. So any morphisms for that? Well, first of all, a simple observation. For any constraint language, if I think of only rational valued functions, there is a constraint language of relations, well, possible on a different set, such that CSP of gamma, counting CSP of gamma, is equivalent, where equivalent means parsimonious reduction, so it's just the answer is the same, to this CSP of this bunch of relations. So in a sense, functions are not so important in this sort of very general sense. Also in a kind of more local sense, they might be very important. But nevertheless, what does it mean? This means that actually we can forget about functions and use our nice, convenient relations and try to do something with relations. What can we do with relations? Well, what can we do with relations? Oh, well, we can come up with a notion of a weaker, even weaker polymorphisms than before. We can talk about partial operations now. And I say that such an operation is a partial polymorphism. Well, if for any choice of tuples from R, if I apply my function, my operation to that, it either belongs to R or doesn't exist. It's partial operation, so it may not exist at all. It may not exist at all. What is good about that, again, p-pol means partial polymorphisms of relation or constraint language. And, well, these partial polymorphisms exactly describe weak clones. Weak clones. So yes, the complexity of anything like this can be characterized by a property of partial polymorphisms. Fine. Is it helpful? Well, of course not. Well, that is a very difficult, this is a very complicated object. So, well, we replaced one complicated object with another complicated object, and basically it says that CSP of relations is as difficult as computing partition functions, then saying that partition functions are as easy as counting CSPs of relations. Okay, can we do something better than that? So, can we do better? Can we come up with some sort of morphisms for these things? Well, nothing known yet. It's kind of strangely difficult somehow, but okay, we can look at options. And actually, every time we look at some option, we get something new. So we learn something about the complexity of counting problems. So, for instance, if we use one of the existing types of morphisms, well, for instance, I don't know, something like submodularity. Well, suppose I have a function. Oh, it should be R. Okay, notation. Oh, okay, so suppose I have a function. I say it's submodular. If I have something like this, which basically means that if I take the log, I say it's logarithm supermodular, log supermodular. If I take the logarithm of both, I basically have the supermodularity condition. Right, so it will be log of f plus log of f less than log of f plus log of f. Well, okay. It's, well, for instance, Farey-Ising is an LSM function, and anti-Farey-Ising is not an LSM function. Actually, David yesterday mentioned these things several times. It's an omega clone, it's useful. It's closed under reductions, so fine. Well, the problem is it's not clear if the same holds for other multimorphisms. Can we replace LSM with any other condition? Sometimes yes, sometimes we don't know, sometimes not, probably. So that's unclear. But nevertheless, even though, well, it cannot be generalized, apparently. Well, we can learn something. For instance, that eventually led to this conservative counting CSP result. Well, I will say that constraint language is conservative. Again, just following David from his yesterday's presentation, is conservative if it contains all unary functions. If it contains all unary functions. Then, well, using that LSM, we can have a almost complete complexity classification of these languages, of conservative constraint languages. Well, I believe about 20% of people in this room were involved one way or another in that. Anyway, so we learn something useful. What else can we do? We can look at the Fourier transform of our function. That might be useful. So that's a very brief definition of Fourier coefficients. Again, okay, I don't want to explain more with that. Just nice transformation, and as we know, very useful. For instance, we can take the set of functions for which all the Fourier coefficients are non-negative. Right? It's a property of Fourier coefficients. Well, then it's a nice omega clone. It's closed under all the gadget reductions. Okay? Can we get something interesting with that? Yes, we can. For instance, there are some interesting constraint languages that are related to this PF and LSM. That's roughly what somebody asked Dave I think, yesterday, if there is a life below LSM. Yes, there is, and some signs of this life come exactly from this clone. So there are things there. What else? Well, maybe we do all wrong. And maybe we shouldn't be pursuing such a strong such strong reductions. Maybe we have to be happy with something easier. Well, for instance, let's relax the closure operator. Right? So let's look at this. Just the basic, very basic weak clone. This is in a sense what Prasad Raghavendra used with his approximation polymorphisms. Okay, so if we follow that route and take Prasad as a role model, what we can do, well, we have to sort of elevate it one level up. We can talk about log approximation polymorphisms of functions. It should be R, right? It should be R. Well, I say it's log approximation if it is a one approximation polymorphism of the logarithm. Again, it behaves nicely with this one, with this weak clone. Well, everything behaves nicely with the weak clone. And in a sense, it worked for Prasad. Maybe it works here. So there are other options as well, again. But the overall idea is that, well, we need find some beauty, right, so that we can, or some concept of beauty so that we can do this, advance in this classification program. Well, clearly gadget reductions are not everything. Well, I haven't mentioned Holland problem here at all. And this is because, well, it heavily use non-gadget reductions, say holographic reductions are not gadget reductions. And so, well, it's not quite clear if they fit into this framework at all. Maybe not. That I don't know. Okay. All right, that's basically what I already said. Okay, thank you.
Question? You've shown convincingly that you can reduce any kind of problem to studying polymorphisms. Do you think it's always a useful thing to do, or and if so,
what do you mean always?
Well,
Definitely not always.
Well, what I'm saying is people do reductions anyway.
Yes.
Why do they need to know that they're doing polymorphism?
Well, my feeling it's always useful for CSP. For other problems, maybe less so.
Okay, so you cannot see any parallel for, say, Holland problems or anything like that?
Well, that's what I said. I have no idea if it fits in any way in this framework.
I mean, is that because you haven't thought about it, or because it...
I don't know. Well, I haven't thought about it, so I don't know. Okay.
Okay, so... any other questions?
I'm kind of wondering, in the omega clone, there's a limit operation, right? And is there any requirement on the convergence speed? Like, if it converges but it's too slow, then I guess still not good for AP reductions.
Yes, it has to be, well, those R's has to be representable by sort of polynomial size. Right, that's true. That's true.
Any more questions? No? Let's thank Andrei again.